very moment your city realized there would be a pandemic, they would be able to simulate every possible scenario that could happen. Instead of trial and error, they would know the best path forward. Now imagine a more calm scenario where you're sitting in your house and you need to run errands. But actually, all the places that you need to go to are right within walking distance of your home. And this isn't just the case for you. It's also the case for every single resident in your city. These are types of problems that are very important to include in a smart city, a city that's designed for your safety, for your comfort, and for your enjoyment, a city that's adaptable to you. But why don't we have such cities already? In fact, the problems that I've mentioned to you, such as disruption management of a pandemic, or resource allocation, or even optimizing the traffic flow, these are all very complicated problems. They're very difficult to do on today's computers. They're very difficult because as the problem grows in size, the amount of time that you need to take to compute the solution grows exponentially. And so as the problem grows, the amount of computing time grows bigger and bigger and bigger, and it rises faster than our computers today are capable of computing. As you can see on this exponential growth graph, as the problem grows and grows and grows, the computation time just continues to increase and increase. It's like if you asked this Chihuahua to win a fight against this Great Dane. The Great Dane is the problem. It's the set of problems that we're trying to solve, and the Chihuahua is the modern computation that we have at our disposal. And so you may be thinking, okay, if we aren't able to solve these problems with modern computers, can we do this with supercomputers, since these are supposedly the most powerful computers that we have available to us today? However, today, these problems can't actually be solved with supercomputers in a reasonable amount of time. It can take these supercomputers even thousands of years, or even the age of the universe, to do these computations. And so what can we do? Quantum computing is a brand new paradigm of computing. These are new computers that are being built based off of the rules of quantum physics. These are the rules that Einstein and his colleagues came up with in the 1920s. These are the rules of the very, very tiny subatomic realm. And it is because we've transferred the computer into this new realm of physics, we have a brand new set of operations at our disposal. This can allow us to do much more powerful computations, to speed up all of the problems that we want to solve. And it allows us to actually do exponential speedups. Like I was saying before, to tackle problems, hopefully such as disruption management or resource allocation. These problems that are really difficult to do on today's computers, on quantum computers can be done much quicker. Problems that can take maybe thousands of years on this computer can take maybe an hour or even minutes. And so, how do these computers work? Today's computers, which we call classical computers, operate on a binary language. They have two fundamental units of information, 0 and 1, on or off. And these are called binary bits. And these bits actually, within the hardware, are very large. You can actually physically hold them in your hand. Now, in contrast, quantum computing, the bits in quantum computers are tiny. You can't even see them with the naked eye. They consist of particles, such as electrons and photons, which are particles within light. And it is with these type of particles that we encode information. And because these particles are so tiny and they're in the realm of quantum physics, we're able to do a whole new set of operations that can exponentially speed up the computation that we can do. Now, you might be thinking, how can we actually manipulate every single electron? How can we actually control them? Because if we can't see them with our eyes, how is this possible? But actually, quantum computers are a reality. They're not fiction. There's a lot of quantum computers that are being built as we speak and that do exist by large industries, industrial companies such as Google, IBM. And they're also collaborating with companies such as Volkswagen, Mercedes-Benz, and BMW to actually explore how can we exploit and capitalize on this new method of computing for the applications in mobility and for applications of building smart cities. And so I'm currently working on one of these use cases, climate prediction. I'm working to see how can we use quantum computers to predict the climate more accurately than our computers can today. And climate prediction is such an essential problem. With climate change, we have increasing climate catastrophes that are occurring as we speak. These catastrophes are displacing human populations due to things like hurricanes and tornadoes. And these catastrophes are also causing difficulties with agriculture. And so what if there was a way that we could actually predict climate very accurately, predict how often or when these tornadoes or hurricanes would actually happen, so that we could warn these people who would have been displaced otherwise and who would have likely undergone various safety constraints. And so climate prediction is a very essential problem for today. And I'm exploring how we can do this, how we can predict climate with quantum computers. And so why quantum, actually? Because we do have powerful computers today, such as supercomputers. But actually, today's methods for climate prediction, for weather modeling, are limited. And these approaches are limited because of two main reasons. The first is the size of the globe. If you think about it, the size of the Earth is very large. And if we actually want to be able to predict climate very accurately, we would hypothetically need to predict the climate on every single point on the globe. And this is a very big computational problem that really challenges the limits of current computation. So for example, current state-of-the-art methods take such a grid. They take a snippet of the Earth, they split it into a grid. And in order to do climate prediction, at every single point of the grid, they predict the climate. But you know, what happens at the points in between these grid lines, in between the points? The space in between actually does influence the weather overall. And so in order to be more accurate, we add more grid points. Now we can do more predictions. And we do this again. But as we want to increase the accuracy, we also increase the power of the computation that we need to use. And so actually, there are rooms of supercomputers just dedicated to this type of computation, to weather modeling. And it's very difficult for today's computers to do this because of the computational capability that this type of problem requests. Now, the second method that is currently limited is the models that we have to predict the climate. The models that we're currently using are limited. And why is this the case? So at the heart of every climate prediction model is an equation. And this, as you can see, is a very complicated equation. It's actually so complicated that one of the most famous mathematical institutions in the world is giving $1 million to someone who solves this equation. So if you want to be rich, solve this. But why is this actually so complicated? This equation is modeling how air moves in the atmosphere. Turbulence. Anywhere from air flowing in the top of the atmosphere to the air that's moving as I wave my hand across the stage. And it's very complicated because this equation takes into consideration many parameters, many variables simultaneously. And to solve this equation, we need to consider all of these parameters at the same time. And this is very difficult for us to do. So while this equation is actually a very good model of the climate that we have, of the weather, it's very difficult to implement in today's computers and to use to actually predict the climate. So here comes in quantum computers. I'm asking the question within my research, can quantum computers predict the climate? And not only can they predict the climate, but can they do so more accurately than today's computers? And I'm doing this currently at the quantum computing company PASQAL in collaboration with the world's largest chemical company, BASF. So again, why quantum computation? Well, actually, there have been a few types of problems that have been shown to this day to have an advantage over classical computers. And these are applications that have been discovered by Google and by a quantum computing company in Toronto called Xanadu. So we have a good direction towards using quantum computers towards meaningful applications. And probably more clearly even, if you can see on this graph that as time increases over the years, we have been able to increase the accuracy of climate prediction models. And this is strongly correlated with the amount of computational power that we have accessible to us. And so if supercomputers have reached their limits, the logical next step is quantum computation. So how am I doing this? How am I using quantum computers to predict the climate? Or how am I exploring this, actually? So we need to be able to make predictions. And a very good tool to make predictions is machine learning. Machine learning builds models that can learn from data, can learn from its environment to make predictions about the world. And machine learning is currently being done in today's classical modern computers. However, I'm using machine learning and quantum computing together. This is called quantum machine learning. Can we use machine learning on quantum computers to really capitalize on the new operations that we have accessible to us at the subatomic level, and to allow for speed-ups and to allow to learn patterns that we otherwise couldn't learn with today's models? And so you might have heard of a term called supervised learning. It's a framework within machine learning that uses examples, uses data to make predictions. It learns from the data set that it has. This is a very common technique that is also being applied to quantum computers. However, I'm not using supervised learning, actually. I'm scrapping the data because sometimes we actually don't have enough data. We don't have enough accurate data at our disposal. And instead, I'm doing something called physics-inspired machine learning, physics-inspired quantum computing. Instead of using data, we actually want to learn the equation itself. So the model will actually be able to understand the underlying physics that this equation describes. And so this could potentially be very helpful, because if we don't have a lot of data at our disposal, we might be able to use this physics-inspired method to perform predictions of the climate. And so how is this being done? So you might have seen in today's machine learning on classical computers, we have neural networks. And these are our models that we use to make predictions. Now, in a neural network, a classical neural network, we have inputs. And the inputs are used to train the model, to update the model's parameters, and to tune it to be able to satisfy an objective that we want. And in quantum computing, we have a very similar paradigm. This is called a quantum neural network. And a quantum neural network also takes in inputs, but it actually encodes these inputs into qubits, into the quantum bits, the units of information within a quantum computer. And because it's encoded in these types of units of information, we're able to do many different new operations on these qubits, on the information that we have provided to us, with the various parameters that you see colored in the middle. These are the parameters that we tune and that we update in order to reach our objective. And our objective in this case is to learn this weather modeling equation. And so this is a preliminary result of the research that I've been working on. This is the use of a quantum neural network, a simulated one for proof of concept, to simulate the weather. And specifically, this is simulating the weather over a patch of Sweden for over 12 hours. And it's simulating something called the stream function, which is the airflow. And in this image, you can see the grid that I was describing before that current state-of-the-art methods are using, where we're predicting the climate. And at each point, you can see the yellow represents areas of high airflow, and the blue represents areas of low airflow. And so this gives us hope that we actually can use quantum computers to predict the climate, because this quantum neural network is able to simulate the climate and to make this prediction of weather. And so climate prediction is just one of many applications that we can use quantum computing for, that we're currently exploring. And climate prediction is so essential to smart cities, but there's also many other applications that are very important to include that are being explored as we speak. So for example, the development of electric vehicle batteries is currently being explored using quantum computers. Chemistry at its fundamental core is very hard to simulate on supercomputers. But on quantum computers, we might be able to simulate chemistry very accurately. We might be able to simulate very large chemical systems. And so currently, there's lots of research being done into how can we design lightweight electric vehicle batteries that save fuel and also allow for more effective transportation. And this is used on quantum computers because at the very fundamental level, to design a battery, we need chemistry, and we need to design new materials. So in this aspect, quantum computing can enable us to explore new materials and to discover new materials. There's also lots of research being done on how can we use quantum computers for autonomous vehicles. Can we use quantum machine learning to actually improve the classification of images that an autonomous vehicle does in order to navigate safely? And there's so many more opportunities to use quantum computing for. So quantum computing is a brand new paradigm of computing. It uses quantum physics to exploit brand new types of operations that our computers aren't capable of doing today. And this can allow us to exponentiate the time in which we solve problems that are relevant for innovating mobility and for creating smart cities. So hopefully, you have learned that there are very complex problems in this world, and that quantum computing can hopefully provide us an avenue to power new innovations and power things like smart cities and mobility. Thank you so much.
Romi, gosh, what a kick-off to our second day. Thank you so much for all of these informations and for also choosing such an important use case. You couldn't know that, but I'm a weather host in Germany, and I know how hard, almost impossible, it is to do a weather forecast for just a week or something. Yeah. So choosing the long-term and climate prediction, awesome. Perfect, thank you so much. I do have so many questions in my head about quantum computing right now, but I will give you the opportunity first to ask any questions. So are there any questions from your side, guys? And just raise your hand and we will bring a microphone to your place. No. Still sleeping, everybody. Okay, then do I ask, Romi. So tell us a bit more about the quantum computers. What makes them so different? What operations do they have that make them so fast instead of the ones that we have now?
That's a really good question. It's very interesting. So actually, quantum computers, there are two main properties that can enable us to do this faster computation. These two properties are called superposition and entanglement. So I like to think a bit of it as, if you imagine the two units of information that today's computers can encode as two rays of light. And for example, you have blue and red. And so you always need to do operations on these two separate entities. However, on a quantum computer, you're able to combine these bits of information into one, such as if you have blue and red on modern computers, you have purple on quantum computers. And so this is able to encode much more information more compactly. And we need to do less operations to work with this information. And so that's called superposition. And that's a really powerful phenomenon that we have in quantum physics, in the quantum realm that I was talking about. And the second one is actually, it's called entanglement. And this is what Einstein called spooky action at a distance. This is where two units of information are connected in space. One can be on the moon and one can be here, but they're connected in some way that when you do something to the first bit of information, something happens to the second
one. Okay.
Exactly. And so these are new types of operations that we can exploit on quantum computers.
Okay, so it's something like, there's a sentence, it calls like, if a mosquito sneezes somewhere, it makes a wave and touches you on the other side of the earth, something like that. Okay, I guess that we all have to focus on quantum computers, especially when talking about businesses, companies, and so on. Yes. So what can they do to prepare for quantum computers? Because it's the next step, obviously.
Yeah, so as I've said, we have reached a limit in our computation. And if we want to be able to tackle stronger problems and larger problems, we need to prepare for it. So there's a lot of things that you can do to really get into quantum computing. From the business side, there's many applications. For example, IBM releases various reports that really discuss in detail the various types of applications that quantum computing can have. There's also, I have a personal website that contains a video series that actually teaches you the basics of quantum computing, what I was talking about, but in a little bit more detail in terms of the physics. So you can learn about the physics, or you can also learn about the various use cases. And what I also like to say is that within the company that you're working at, try to see where are there problems that are very complicated to do and that are requiring a lot of time, and then reach out to various companies to see how quantum computing can actually help in these aspects. And this will allow you to prepare for when quantum computers are very, very powerful.
But not only as a company or for a business, me, myself, where can I learn more about quantum computing? Where do I start?
Good question. So my YouTube channel is called positthis.com, posit-this, and that contains a video series. So it starts about classical computers, talking about bits and how they're used. And then it talks about quantum bits, the qubits that I was talking about. And so this is a very friendly introduction. You don't need any background in physics to understand it. It gives you all the necessary requisites, and so I would recommend to start there. And also, there's just so many resources, like I was mentioning IBM. It's called IBM Qiskit. So if you search up IBM Qiskit, there's a lot of really cool resources that are at your disposal.
That's what each and every one of you is doing in the next break.
Yeah, very interesting.
So final question, is there anything I can do, we can do, society can do to help advance the development of quantum computing? Anything we can do? Yeah, there's plenty. So first of all, we need to raise awareness about quantum computers because this is a very new technology. And so both within businesses and within our personal interests and use cases. So first of all, raise awareness. Second, try to find technologies and problems that are very challenging. And even yourself, try to think about why is this so challenging? And you can even write blog posts about this. You can even advertise this on media. Just make it raise awareness that quantum computers are actually here, and they're not fiction. We actually have, as you saw, quantum computers that are present at the moment. But I will say that there's a long way for quantum computers to go. They are capable of so much potential, but there's a lot of research that needs to be done at the moment. So supporting this research is really essential to be able to achieving all of these different applications. Thank you so much. So I'm still checking if you have any questions, guys. No, you don't. Okay, then Romi, once again, thank you very much. That was an amazing kickoff. We couldn't wish for a better one.
Thank you so much.
Thanks a lot for all of your insights.
Thanks, everyone.